In this lesson, we will learn one important technique that is widely used in speech signal processing. Pitch estimation is also called pitch detection. Voiced speech is interpreted as a concatenation of slowly evolving pitch cycle waveforms. Pitch period only exists in voiced speech waveform. As is shown in the figure, TP is pitch period, FP is fundamental frequency, FP is the inverse of TP. We can observe pitch period from the speech waveform in time domain and observe the fundamental frequency from the narrowband spectrogram. Pitch can make it possible to judge sounds as higher and lower in the sense. A reasonable definition for the short-time autocorrelation is shown with function Rk. The first step is to select a segment of speech by windowing and then to compute deterministic autocorrelation of the windowed speech. As is shown in the figure, the window length L points is used to compute R0 and L minus K points is used to compute Rk. We can define filter of the form WKM. This enables us to rewrite the short-time autocorrelation in another form. The input signal Xn is delayed by K samples and multiplied by the delayed signal xn minus k. The short-time autocorrelation Rnk can be obtained by filtering the product sequence xn times xn minus k with a filter with impulse response wkm. The autocorrelation function using different types of windows are shown in these two figures. Figure A and B are the results for voice speech, and C for unvoiced speech. Autocorrelation peaks occur at k equals 72 and 144. Thus, the fundamental frequency is 140 Hz. The values at pitch cycles are smaller than that at 0, since window speech is not perfectly periodic. Over a 401 sample window, that is 40 milliseconds of signal, pitch period changes occur, so pitch cannot be perfectly defined. There are much less clear estimates of periodic, since Hamming window tapers signal so strongly, making it look like a non-periodic signal. There is no strong peak for unvoiced speech. This figure shows short-term autocorrelation and spectrum of one voiced speech segment. T0 is the pitch period. F0 is the fundamental frequency. The autocorrelation function has several peaks on the positions of pitch period and its multiples. The window size affects the pitch estimation result. It should be chosen properly. When the window length L is small, pitch period is almost constant in window. When the window length L is large, there is a clear periodicity seen in window. As k increases and the number of window points decrease, the accuracy and size of the autocorrelation function Rnk for large k is reducing. In applications, the window length should be allowed to include at least 2 full pitch periods. In the algorithm of pitch detection based on short-time autocorrelation, center clipping is usually used to pre-process the input speech segment. The autocorrelation function of the speech signal has a sharper peak after pre-processing with center clipping. After the pitch detection, the post-processing will be done to smooth the pitch period trajectory. We can say median filter, linear filter, or combination smoothing methods to remove the outliers of pitch computation. To solve the problem of differing numbers of samples for each different k term in autocorrelation function Rnk, the definition of autocorrelation can be modified to be another form with an extending window of duration L plus k samples, where k is the largest leg of interest. Thus, there are always L samples in computation of autocorrelation function. Another method to estimate the pitch period is short-time average magnitude difference function, AMDF. For periodic signals of period p, the difference function is expressed with dm. It will be approximately 0 for k equals 0, negative positive p, negative positive 2p. For realistic speech signals, dn will be small at k equals p, but not 0. Thus, we can define the short-time average magnitude difference function with the difference of the successive input signal weighted by rectangular window. If both windows are the same length, then AMDF is similar to the short-time autocorrelation, whereas if W2 is longer than W1, then AMDF is similar to the modified short-time autocorrelation or covariance function. Here is the AMDF function of one-voiced frame. The pitch period is about 42 samples or points. The valley point of the pitch period is sharper than the peak point, and the estimation accuracy is higher. The calculation of the short-time AMDF does not require multiplication, and the calculation amount is small. AMDF is sensitive to rapid changes in speech signals. Pitch represents the characteristic of the sound source of the speech production model, which is important in speech signal processing. In speech parameter coding, the fundamental frequency represents glottal excitation, which is important for sound quality. In speech recognition, pitch tracking is used for intonation recognition, which can be used to eliminate the ambiguity of homophonics. In speech synthesis, pitch tracking is used to correct the prosody of the speech segment and solve the problem of tone changing in spoken language. It also represents the tone and intonation. In speaker conversation, changing the fundamental frequency can convert one speaker to another. For example, male voice has different fundamental frequency from female voice. In real application, pitch detection is difficult because of the unvoiced-voiced ambiguity. Frequency multiplication, division, precision, and time varying of pitch cycles. There are also some other methods in research to solve the problems of pitch detection. That's all for this chapter. See you next chapter.